You want to say hi to Martin.
Yes, okay.
Probably you'll get a lot of hands being raised
Yeah.
instead of asking a
But
question.
we can do that at the end. We can do that at the end of the talk.
But at the end, when I turn off the slides, we can get more pictures.
Yeah, do that.
So I can only see you two at the moment. You.
Yes, that's because I think
Can't do,
all the other people's videos have been turned off and they've all been muted. So, yes.
We exercise our privilege. We, as a host, we can turn off people's videos and audios.
I can also turn off the video. And that's it. Okay.
We just wait. I won't delay you too much. I'll give you a very short introduction. You don't need an introduction. So.
Okay. Yes, and then I won't adjust my screen because already you can see my slides. Is that right?
Yes. Do you just try whether you can go to the next slide?
Okay, but let me just see if I can.
You either do the arrow or do the enter mouse.
So,
it's not moving, is it?
Yeah. No, I can't go to the next slide.
Good. So either the side arrow or the arrow.
Hello, sorry to disturb you. You just click on the slide because I think so that window is deactivated.
Can you just click on the slide?
Click on the slide?
Yeah, just click on the slide. Yeah.
Just a minute. Yes. Okay.
Yes.
Then you can go back. Yeah.
Okay. Oh no, it seems to work now on my keyboard as well. Yes.
Okay, great. Thanks.
Okay. Yeah. No, I had a terrible time 2 days ago when there was something on software called Webinar Jam, and I had to cancel a lecture because it was on Chrome rather than on Safari, and I didn't deactivate Safari, and it, as I realized, but I just couldn't get this to work. It's so frustrating. But now it's okay.
No, the other problem that might happen is sometimes the internet connection is flaky, and I was a little nervous because we had a little thunderstorm here just before.
Oh, right. Yes. Okay.
Now things will be all right. I mean,
let's hope
but there are a large number of people like there will be today.
Yeah.
At our end, if the internet connection isn't very good, sometimes they can. But
it seems
I should be all right.
Just before the talk and stop just before the talk.
Yeah. No, on Thursdays we've been doing this, and several others have given this talk from Europe and the UK, and in general we haven't had any problems. So let's fingers crossed. So we will start. I'm just waiting for more people to join. Great, we can start. Welcome everybody. I see we have a lot of people here today. Welcome to the IUCAA Thursday afternoon colloquium. Thank you very much for coming. We are also live on YouTube at the same time, and I can see a very large number of people there as well. It's absolute privilege for me to welcome Professor Martin Rees to today's lecture. In fact, when we went online in this mode, and this opened up the opportunity of inviting people who are physically not here to give this colloquium. The first person we thought of when I was why don't we try and see whether Professor Martin Rees can come join us. Martin has been one of our friends for a very long time. I just calculated, I've only known Martin for 35 years myself. And of course, from the time when I was a student, and Martin has been a great mentor for me personally and for many people here at IUCAA over the years. in our interactions. Martin is, of course, the Astronomer Royal, and until not so very long ago, he was President of the Royal Society and Master of Trinity College, and now is still at the University of Cambridge, and he really needs no introduction. So I'm not going to prolong the introduction by saying any more. I would like, as I said, I'm very happy to hand over the mic to Martin, talk about progress and frustration in cosmology. Martin.
Well, Shamak, first let me say what a pleasure it is to be linked in to you all. I wish I was with you in person, but it's a great pleasure to be able to interact with you this way. And I bring greetings from all my colleagues in Cambridge. And I thought I'd start off with a bit of history. This is Trinity College, Cambridge, and this has been there for many centuries. And this is the best student we ever had there, Isaac Newton, of course. And I show him because we depend on his insights every day. And he must have thought a bit about space travel, because this is a famous picture from his Principia showing a cannonball being fired from a mountaintop. And if it's fired fast enough, it goes into orbit. And this is still, I think, the easiest and clearest way to explain to students the concept of orbital flight. But he knew you had to fire the cannonball at 18,000 miles an hour to get into orbit, and that, of course, couldn't be done until Sputnik in the 1970s. So that is Newton. Coming a bit closer to the present, this is a picture taken in about 1931. It shows on the right Arthur Eddington, who was a professor in Cambridge, and on the left, you know who that is. They're probably talking about the Eclipse expedition, which 10 years earlier Eddington had led to test the light bending, or perhaps about the new theories of the universe, because even by then we had the standard Friedmann and Lemaitre models for a homogeneous expanding universe, but astronomers didn't have enough evidence to know which of them is correct, nor indeed whether the universe had the properties needed, whether it was homogeneous, etc. So these were speculations back then. And of course, the other person I should mention is Chandrasekhar, who was a student of Eddington, but of course famously had rather unhappy experiences there, and went to Chicago, and I'll mention him again later because he was a key figure. This is another historical picture which shows a debate between the Big Bang theory and the steady state theory. This was taken in the 1950s, and on the left is Fred Hoyle, who believed in the so-called steady state theory and was never reconciled to the Big Bang. And on the right is Lemaitre, who in the 1920s was the first person to talk about the so-called primordial atom, as he called it, the Big Bang. And at this time, in the 1950s, he was president of the Papal Academy of Sciences and was an advocate of the Big Bang. So this is a nice historic picture. And if we think of astronomy, it had a real renaissance in the 1960s, especially with relativity. And there were really three main groups. There was an American group led by this man, John Wheeler. And there was the British group where the key figures were Roger Penrose, who's alive, he's 89 years old now, and Stephen Hawking, who was really a student of his, and a student of Dennis Sharma. And these really pioneered the group of astronomers in the UK. Who developed many of the key ideas of relativity. And in the Soviet Union, there was an equally strong group led here by Zeldovich, who in parallel did a lot of the exciting work of the 1960s, understanding the nature of black holes, etc. Well, before going further, I thought I'd just give a list of the main reasons why we do astronomy, because my talk is going to probably touch on all four of them. First, we just want to find out what's out there, just do exploration of everything from the solar system to the remote universe. But that's a step towards trying to interpret what we find in terms of the known laws of physics and perhaps learning new physics or testing physics under extreme conditions. And then we want to actually see if we can understand how the universe came to be the way it was. How from a simple beginning did our universe evolve into the present complex cosmos of which we are a part. And then even we'd like to perhaps get a bit more philosophical and see if we can understand the key properties of our cosmos in any deeper way. So I'll come on to that at the end. Can I ask, is the sound all right? Can people hear what I'm saying? Yep. Okay.
Yes,
okay. Let's get into the real universe. If we could get 3 million light years away from our Milky Way galaxy and look back, we'd see something like this. This, of course, is the Andromeda galaxy. It's a spinning disk viewed obliquely. And here's another galaxy, Whirlpool galaxy, a disk seen head on. And we know that the main ingredients of the large-scale universe are galaxies, and this shows a map of the galaxies within 400 million light years, indicating that they're not randomly distributed, they're grouped together in clusters. But on a very large scale, their distribution is fairly uniform. And another thing we've learned about these galaxies is that, as I mentioned, they have black holes in their center. But you might want to know, how can we learn to understand anything about galaxies? Because if you were a physicist dealing with particles, you'd crash them together and see what happened, things like that. And we can't do experiments in astronomy. And of course, in a galaxy, everything changes slowly. It takes about 200 million years for an orbit around the central hub of the Andromeda or our galaxy to take place. But we can do experiments in the virtual world of our computer. And let me show you one here. This shows a collision between two galaxies. The input here is gravity and gas dynamics, and two galaxies are falling together, and a sort of train wreck, and it'll settle down into an amorphous elliptical galaxy. And I should warn you that this is going to happen in about 4 billion years when the Andromeda galaxy hits our galaxy. After that time, there will be a mixed up mess of stars like an elliptical galaxy. Well, this is just a simulation, but if we look in the universe, then we see things like this. This is a pair of galaxies, and having done simulations like I showed you, we can guess that what happens here is that the two galaxies got close, and one has pulled out a tidal plume from the other. And if we could come back in 100 million years, we'd probably find that these two had merged, as in the movie I just showed you. And indeed, we've learnt a lot about galaxies simply by doing simulations, making different assumptions about the number of stars and also about whether there's any dark matter there, etc. So we've come to understand the existence of galaxies. Now, one thing we can do is we can look a very long way away in the universe, and this picture shows only a few arc minutes across patch of the sky. It would take 100 patches like this to cover the full moon, but in this tiny patch there are hundreds of little smudges. Each is a galaxy, many fully the equal of our galaxy, looking so small and faint because of their distance. They're being viewed more than 10 billion light years away, so we're seeing them when they're young. So we can test our theories of galaxies, not just by looking at a lot, but by looking at them 1 billion years ago, 2 billion years ago, etc., by looking out into space and therefore back into time. And that's how we've come to understand quite a bit about galaxies. And we can look very far out. The object highlighted there is an object with a redshift of about 7. And this is its spectrum, the optical trace of the spectrum. And I show it because on the left, there's a strong line. And this is the Lyman alpha line of hydrogen, which is normally in the ultraviolet, 1216 angstroms. But here it's in the red. It's stretched by a factor of 8. between emission and reception by the expanding universe. And so we know this object is very, very far away. This spectrum actually shows not just the starlight from a galaxy, but it shows a quasar where the starlight is overwhelmed by emission of hot gas in the center of the galaxy. That gas is being energized not just by stars, but by a huge black hole. This is a computer simulation again, showing gas swirling down into a huge black hole. And we know that galaxies have lurking in their centers black holes, weighing, in the case of our galaxy, about 4 million times as much as the sun, but in other galaxies, many billions as much as the sun. And you may have seen in your newspapers last year this picture, which is actually a radio map showing with rather poor resolution the region around a black hole in a nearby galaxy. And if you interpret this, you can find it does provide evidence, as do other observations, that black holes exist, and they have the properties which you would expect if Einstein's theory were right. And it's even more remarkable than that, in that they all these black holes are consistent with having the properties which were first calculated by this man, Roy Kerr. He's a New Zealander, and he, in the 1960s, found a solution of Einstein's equations, which he conjectured represented a spinning object. And thanks to the work of the people I showed earlier, Penrose, Hawking, and others, we now know that every black hole, once it's settled down after formation, is described exactly by these equations. And this is something which hugely impressed Chandrasekhar. He says that it was quite amazing to realize that out in the universe, there are billions of these objects which can be described exactly by these equations, the equations first discovered by Roy Kerr. I should say that we're trying to refine, obviously, our understanding of how gravity behaves under extreme conditions, but I think everyone will accept that black holes exist in the centers of galaxies and in other contexts, and it does seem that Einstein's theory has survived all the tests, which is really great. Well, if you look very far out and far back into space, you eventually look back to a time when no galaxies had formed. So what do we know about the early part of the universe? And here again, as probably everyone knows, we had a big breakthrough made by these two characters, Penzias and Wilson, using a dish at the Bell Telephone Labs in the US. They found that intergalactic space wasn't completely cold. It was warmed to about 3 degrees above absolute zero by microwaves pervading the whole of space, coming from all directions. And it was subsequently realized that this radiation filling all of space had an almost exact black body spectrum, and it was interpreted then as what's poetically called the afterglow of creation, the cooled radiation left over from the hot, dense beginnings of the universe. As the universe expanded and cooled, then this radiation wavelength stretched, it went to lower temperatures, but it fills the universe, it's got nowhere else to go, and it's still around to be observed. And this radiation has been observed with great precision, black body spectrum, and it has led with other data to what I call the standard hot Big Bang model of the universe. This is a time chart where time is measured vertically, and if we look back, as I say, we see back to a time before the first galaxies formed. They formed when the universe was maybe a few 100 million years old. But we can actually look back to when the universe was about 300,000 years old. The reason for that is that that's the time when the background radiation, now at 3 degrees, was about 3,000 degrees. And when it's above 3,000 degrees, everything is ionized, and it's like being inside a star. It's all very opaque and foggy. But after that, the hydrogen gas recombines, and the radiation can percolate freely. So when we look at the universe with the microwave background, we see back to when it was about 300,000 years old and about 1,000 times more compressed. And although I don't have time to go into it, we have very good evidence for what the universe was like when it was a few seconds old, because then it was hot enough for nuclear reactions to occur, and in particular for hydrogen, helium, and deuterium to be produced. And the proportions predicted agree very well with the proportions that were observed. But first, let me address an issue that might seem puzzling. Our present complex cosmos manifests a huge range of temperature and density, from blazingly hot stars to the dark night sky. And people sometimes worry about how this intricate complexity emerged from an amorphous fireball. It might seem to violate the second law of thermodynamics, which describes an inexorable tendency for patterns and structure to decay or disperse. But the answer to this seeming paradox lies in the force of gravity, because gravity enhances density contrast. A slightly overdense region in the expansion lags behind more and more and eventually separates out and condenses. And many simulations have been made, and this is one, and this shows a segment of an expanding universe where the expansion is subtracted out, but you see the density contrast growing and some regions collapse. And this shows in blue the dark matter, and in red the ordinary atoms, which are destined in this one to turn into a galaxy and then into stars. So within each galaxy scale clump, gravity enhances the density contrast still further, gas is pulled in and compressed into stars. Now, there's one important point here. In that simulation, the initial conditions fed into the computer model aren't arbitrary. They're derived from observations. They're derived from the observed fluctuations in the temperature of the microwave background. If you look at the microwave background over the whole sky, as I said, we're looking back to when the universe was in a pre-galactic era, 300,000 years old. This contour map shows that some patches are slightly hotter and some are slightly cooler. The range is small. It's about 1 part in 100,000, 10 to the minus 5. But the density contrasts grow, and it's from these fluctuations that we end up with our present universe. And just to quantify this a bit, this is a diagram due to Max Tegmark, which says that if you feed in fluctuations like we observe and then run the computation forward, then the root mean square fluctuation amplitude as a function of scale should follow the continuous line. And there are various sets of data which fit on different parts of that line, so there's a good fit. So what is rather remarkable is that we are able to understand how the structures we see in the universe today emerged by clustering of the gravitationally dominant dark matter during cosmic expansion. Incidentally, just to introduce a complication, if you look in detail at the angular fluctuation and see how large amplitude is on different angular scales, you get data like this. Large angles on the left, low harmonics, and these on the right. Don't have time to go into this, but what I want to emphasize is this is a real triumph of theory and observations, because the theory allows us to predict this complicated curve, which is due to sound waves and things in the early universe. And the observations, as you can see, have such small error bars you can barely see them. So a calculation of what this radiation should do and what happened in the early universe predicts the amplitude as a function of the harmonic number, which means the angular scale. And one particular thing I do want to mention is that there's a big peak, the one on the left there, and this corresponds to a wavelength which has been able to make a quarter of an oscillation as a big sound wave. before the matter recombined. And this is a very important sort of length scale in the universe, which I'll come back to again later. Well, let's go back to this time chart of the universe. As I said, we have direct observations of the microwave background back to 300,000 years. We have pretty firm evidence of what the universe was like when it was a few seconds old from nuclear reactions, which we can calculate and which agree with observed proportions of hydrogen and helium. And I would claim that we can probably extrapolate with confidence back to when the universe was a nanosecond old. I say a nanosecond because that's the time when the average particle in the universe zooming around would have had about as much energy as could be produced in the biggest accelerators, like the Large Hadron Collider in Geneva. When you get back within the first nanosecond, still earlier, still lower in this time chart, then things get more speculative because we lose our foothold in direct experimental physics. We don't know what happened very, very early on. However, if we want to answer many fundamental questions about the universe, such as what caused those fluctuations? Why is the universe filled with these sort of ripples and fluctuations and sound waves? Second, why does the universe expand the way it does? And third, why does it contain the observed mix of atoms, dark matter, and radiation? We have to probe back further, because we can't get the answer without some new and uncertain physics, which involves going back to the first nanosecond. And here I put up a hazard sign because everything about this very, very early stage is much more speculative. And a common idea, which goes back now nearly 40 years, is that at a very early time, when the universe was about 10 to the minus 36 seconds old, and when the whole volume we could see with our big telescopes was shrunk down to the size of a tennis ball, it's thought that there was a change in the physics which led to an exponential expansion. So something microscopic expanded in its tiny, tiny time scale to become large enough to produce our entire observable universe. This is called inflation. And on the basis of this, we can understand the fluctuations we see spread across the sky in terms of quantum fluctuations when the entire universe was of microscopic size. This is a really mind-blowing idea. But we really do think that this was this is realistic. It's not battle-tested physics, but there are reasons to take it seriously. But it won't be firmly established until the physics of that very early era can be confirmed by predicting its consequences at low energies and actually having observational tests, which tell us something about the unified theory whose crucial manifestations are way beyond where we can directly observe them. So let me see how we're getting on. Well, as I said, we believe that our universe and its fluctuations can be traced back to this tiny early era. But 20 years ago, astronomers had a big surprise, which didn't affect this idea about the early history of the universe, but did affect our ideas of what would happen in the far future. We've known in principle, ever since Lemaitre and Friedman, that there are three different scenarios for an expanding universe. And here we have time plotted upwards and three possibilities. On the left, we have the idea that the universe expands, but the amount of gravitational attraction between one galaxy and another eventually decelerates the expansion, so it stops and collapses back to a big crunch. In the middle, there's the case which involves, again, a deceleration because of the gravitational pull of every galaxy and every other galaxy, but that's not enough ever to stop the expansion. But there's a third scenario, which is speculated about, and that's the idea that in empty space, there's some mysterious force over and above gravity, a sort of repulsive force, which drives things apart. That's unimportant in the early universe, unless it was then much stronger, as it was in the inflationary era. But at late times, on intergalactic scales, this cosmic repulsion overwhelms gravity. And so the galaxies would then start moving apart at an accelerating speed. And this idea was not taken very seriously until 20 years ago. So it was a big shock when observations revealed that this theory seemed to be correct, that the universe was indeed expanding. The most direct observations were from just doing the Hubble law, looking at the redshift versus distance and finding that at large distances, the expansion was faster, not slower. But there's another indirect way, which I will mention, which is going back to this picture here. The high peak, which represents the scale of a sound wave at recombination, that has an angular scale, which depends on the geometry of the universe. It's a rigid rod, and if we are in a hyperbolic universe, then it's got a certain scale. If we're in a flat universe, by which I mean a universe where the angles of even a very big triangle add up to exactly 180 degrees, then it's got a bigger angle. And this angle, where that peak occurs, if the universe just contained atoms and dark matter, which is 30% of the so-called critical density, would be on an angular scale of about 0.2 of a degree. It's actually on a scale of 1 degree, which indicates the flat universe, and that means there must be something else in the universe flattening it. And I think this is an extra argument, which in my view firms up the arguments for the acceleration. If we just had the supernovae, frankly, I'd still be skeptical. But there's this network of arguments. We have the straight evidence from the Hubble law, that's indicated at the bottom, which implies acceleration. But we also have this indirect evidence, which is slightly more technical, but let me just mention it, that the angular scale of that Doppler peak indicates a flat universe with omega of 1. But we know from other arguments that omega of dark matter and atoms is only 0.3. And there must be something else making up the other 0.7. That something else must be uniformly distributed. Moreover, it must be something which was less important in the past than now. Otherwise, galaxies would never have formed. That means it must have negative pressure. As it expands, the pressure has got to go down. And in Einstein's equations for an expanding universe, negative pressure gives acceleration. So in principle, if we just had that evidence from the microwave background, we could have predicted the acceleration. And if we tie it together, then we have, I think, a convincing model that the universe is accelerating. Now, this energy latent in empty space, which in modern guise is something, quantum fluctuations in empty space itself, I think it's going to be a big challenge before we ever understand this. And the reason is that although no one really has a unified theory to explain it, nearly everyone agrees that just as ordinary substances have a structure when you get down to atomic scale, then space itself and time have a certain graininess if you get down to a certain scale. But that scale, which is a scale where gravity and quantum effects overlap, is 10 to the minus 33 centimeters, a billion times smaller than an atomic nucleus. And so it's only on that scale that space itself has this complicated structure. And of course, there are theories like string theory, loop quantum gravity, which are trying to understand this, but we're a long way from those. So even though I hope we'll understand what the dark matter is, I'm not at all optimistic about understanding this mysterious dark matter, which is causing the universe to actually accelerate. And just to make a sort of curmudgeonly remark at this stage, first I should have said that the far future that's predicted is one in which the universe gets ever colder, ever darker, ever emptier, because distant galaxies disappear over the horizon. But I wanted to say that this particular diagram, which is very familiar, which shows the proportion of the mass energy in the present universe in the form of dark energy, dark matter, and ordinary stuff, it's been used very much, but I think it's a bit misleading. And the reason for that is that this is true in the present universe, but if you extrapolate back in the past, the ratio of dark matter to atoms stays constant, but the dark energy, which doesn't go up as you go back to the past, gets less and less. So in fact, at any time in the first half of the universe's history, which is a time when all galaxies and things form, the dark energy didn't play any role. And of course, these dark energy repulsion is only important in intergalactic space. It has no effect in galaxies, still less in planetary systems. So although the dark energy is perhaps the most fundamental problem for physics, dark energy is pretty irrelevant to all of astrophysics. It's irrelevant if you want to understand how galaxies form, how they evolve, what goes on inside galaxies or clusters, whereas the dark matter is crucial to all of those. And so I think this sort of diagram, which has been used as a poster child for those who want to study the dark energy, is a bit misleading in that it's not representative of the relative importance of those to astronomers, although it is to physicists. Well, let's turn to another basic question. How big is the universe? Well, we only see a finite amount of material in the universe. We look out with our telescopes and we see billions of galaxies, but there is a limit. And even if we had an infinitely powerful telescope, we wouldn't really see back further. We're limited, and that's because there's a horizon around us, which is set by how far light can travel in the time since the Big Bang, crudely speaking. And that horizon, though, has no more physical reality than the horizon around you if you are on a boat in the middle of the ocean. There's a shell around us, which is a limit in principle to our observations, and just like there's a circle around us if you're on a boat in the ocean. And on the ocean, you don't really know what lies beyond the horizon, but you certainly don't think the ocean ends just beyond your horizon. Likewise, there's no reason to think that the universe of galaxies ends at our horizon. Indeed, there are strong indirect reasons to expect that galaxies go on much further than we can see. In fact, a quite good evidence it goes on at least 100 times further than we can see. And it may go on much further than that. Sorry, this slide isn't very clear, but this is just to make the point that beyond the horizon, it could be that galaxies go on so far that all combinatorial options are fulfilled. And so there's another set of people like us in the same way, and you have your avatar, and if you make a bad decision, it may be some consolation that far beyond the horizon, there's some avatar that's made the right decision. So that's certainly possible. We don't know, but it's possible that the universe is so extensive that the amount beyond the horizon completely overwhelms what we can see. And that's not all, because all the galaxies I've talked about so far are, as it were, the aftermath of our Big Bang. But there are many theories which suggest that our Big Bang was not the only one. In particular, there's one idea which is illustrated by this cartoon. And this cartoon on the bottom right, you see, roughly speaking, our horizon. It's about 14 billion light years, we think. And beyond that, lots of galaxies. But in the grandest perspective, all this, the aftermath of our Big Bang, is just one domain of space-time in some ensemble, some sort of archipelago, which may contain huge numbers of different Big Bangs. And this is just one manifestation of a set of ideas which are called the multiverse. Well, this is an idea which is due to Andrei Linde, a Russian cosmologist now at Stanford in the US. And the idea here is that our Big Bang is just one among many. Well, of course, some people say, well, how do we know that these things could exist? Is it science even to talk about them? And I would say that it may be speculative science, but it's science, not metaphysics. Let me give an example. We can't observe the inside of black holes, but we believe what Einstein says about them because his theories gain credibility by predicting correctly what we observe in many other contexts. Now we don't know, but if we did have a theory which described physics at 10 to the 16 GeV, that's the energy when inflation occurred, and if that theory could be vindicated by predicting things we can test, by, say, predicting the 3 kinds of neutrinos, what their masses are, and things like that, then we take it seriously. And Linde has shown that if it has particular properties, then inflation will lead to this so-called eternal reproduction of universes. So I'm not saying that there's any evidence yet, but I'm just saying that this is a possible scenario which must be considered among the various different ideas for what happens in our early universe. So what I would say is that for 21st century physics, a big challenge is the following: to see which branch of this decision tree is correct. How many Big Bangs are there? If there's only one, that's on the left, then of course that's it. It cooled down and was governed by the present low energy physics. On the other hand, if there are many, then there's an interesting possibility which is suggested by some varieties of string theory. Some varieties of string theory suggest that there are different vacuum states and that the universes may cool down differently and be governed by different physics when they get down to low energies. And so if that's the case, then these different Big Bangs would cool down, giving rise to universes that could be very, very different from ours. And then this leads to the idea of so-called anthropic selection, because we would then calculate what these different universes were like, and we'd find that some of them would allow the sort of complexity which has allowed us to observe, whereas some would be sterile and stillborn because they wouldn't have the kind of physics which allows complexity of any kind, and therefore any kind of brains and thought to evolve. Well, this is called anthropic selection, which is something which would be forced upon us if the right-hand side of the decision tree were correct. And I should say that some people sort of foam at the mouth at this term completely. They say it's not physics. But for any of those who are listening now, I'd like to say that quite apart from the anthropic motivation, some physicists find it helpful to develop their intuition by exploring what would happen if the laws of physics or the parameters of the universe were different from their actual values. It's rather like counterfactual history, where some scholars speculate, for instance, on what might have happened if no Brits had ever gone to India, for instance. Or biologists speculate about how our biosphere might have evolved differently if the dinosaurs hadn't been wiped out. So if you don't like anthropic selection, then take what I'm going to say now as just a counterfactual history, which will tell you how our universe's properties are sensitive to particular numbers. And incidentally, I'm going to deflate some of the ideas of fine-tuning, which have often been discussed, by talking about virtual universes, which are slower, smoother, more chaotic, darker and less polluted than ours. Well, first, what if gravity had different strength? Big G, the fundamental number, were different. Well, this is an interesting question, and it's best explained by this, which is my favorite pedagogical diagram, which is taken from a paper I wrote with Bernard Carr a long time ago. This diagram shows the log scale, radius along the bottom and mass along the top. And there's a line for black holes, which has slope 1 on the log-log plot. And there's a proton at the bottom, and there's an atom, which is along there. Solids, which all have a density of 1 atom per Bohr volume, they lie on a line of slope 3 going up from the hydrogen atom. And so we have sugar lumps, humans, asteroids, planets. And there's also the quantum uncertainty line, which goes inversely with mass. It's because gravity is so weak that you need to have a big black hole, a big mass to make a black hole. A black hole, the size of a proton, has a mass of about 10 to 38 protons. You see from there. And this is why, incidentally, the Planck scale, which I mentioned earlier, is very much smaller in the scale than the size of a proton. So if we go back to this, we can see that on the line, which contains humans, the Earth, etc., then that line is getting closer to the black hole line. So gravity, which has a handicap of 10 to 38, because it's so weak, it eventually wins, because everything has the same charge, as it were. There's no cancellation like electric charge, and so it powers up for bigger objects. And so when you get above the size of the Earth, up to the size of Jupiter, then you find that gravity is able to crush something, and it turns into a star. And to give an expansion of that, this is familiar to anyone who studied evolution. It shows the scale of white dwarfs and stars, etc. But the reason I show this is that if you were to make gravity stronger or weaker, the shape of this picture would not change, but the scales would change. If you make gravity stronger, then stars would exist, but you wouldn't have to pack so many atoms together for them to be crossed by gravity. So you get a small scale speeded up universe. You'd even have small stars, gravitationally bound fusion reactors. They wouldn't last very long. On the other hand, if you make gravity weaker, then you can have even bigger stars lasting even longer. And indeed, although a universe which was small in scale and where stars were small because gravity was strong would not be conducive to life, if big G were weaker, then this might be an even better universe for life, because supposing big G was 1,000 times weaker, then the characteristic masses of stars, the Chandrasekhar mass, etc., they'd be 1,000 times greater. Stars would live 100 times longer. And so there might be far more time for complexity to evolve, and things will get bigger before being crushed by gravity. And indeed, incidentally, in that model, if you kept the other parameters the same, you would find that galaxies would also scale up in the same way. So it'd be the same number of stars in a galaxy, but the galaxies would weigh 1,000 times as much, and each star would. The only change, actually, in cosmology, if you were to make gravity much weaker, is that the hydrogen-helium ratio would be different, because the time scale when the universe was hot enough, nuclear reactions would change. So the point I want to make here is that gravity needs to be weak in order to allow a complex cosmos. If small things are crossed by gravity, you can never build up large stable structures. But there's no fine tuning. And indeed, if gravity were weaker than it actually is, this might allow an even more interesting universe. So let's now turn to another parameter. I mentioned that the fluctuations in the early universe are important as seeds for galaxy formation. And I showed you a picture of what they are. And roughly speaking, their amplitude is about 10 to the minus 5. This is a number we call Q. And this number, which is an average size of the fluctuation on relevant scales, is very important, because this means that if a structure can condense out under gravity, its virial energy is Q times mc squared, and the virial velocity is about Q to the 1/2. So a cluster of galaxies has a virial velocity of about 1,000 kilometers per second, which is 10 to the minus 2.5 of c. And also the largest linear scale, which goes non-linear as the universe expands, is then Q to the 1/2 times the Hubble distance. So that means that the universe has non-linear amplitude fluctuations now on a scale up to about 10 megaparsecs. So what would happen if Q were different? This is from a paper I did with Max Tegmark some time ago, and let me just give you 3 examples. First, let's take what I call an anemic universe. This would be if the fluctuation amplitude were less. Then it would take much longer for any system to separate out, and they'd all be more loosely bound. And galaxies and their halos would have a lower escape velocity, and matter would escape, so you wouldn't really get so much efficient star formation, etc. And if Q was even less than 10 to the minus 6, then you wouldn't get any bound structures forming at all. On the other hand, let's suppose that Q is 10 times bigger than it actually is. Then you get again a rather interesting universe. You'd find that masses as big as, say, the Coma cluster, they'd condense out, they'd go non-linear at a redshift of 10, and they would form huge disk galaxies, because Compton cooling would cool the gas down there. So you'd have, at redshift of 10, huge disk galaxies of 10 to 14 solar masses, and now you would have clusters of 10 to 16 solar mass containing these things. And so this would be, again, a rather more interesting universe than the one we are now in. But if Q were even bigger, say 10 to the minus 3 or larger, then you get a rather chaotic universe, because then what would happen is large black holes would form very early on, and probably it would be a very sort of violent universe where, again, stars couldn't form very easily. And of course, one other point that's important is that it's only because Q isn't too big that we can use the standard cosmological models. Because if we were in a chaotic universe, it would be rather like being in a mountain landscape rather than being on an ocean. The difference there is that if you're on an ocean, the biggest waves are still small compared to the horizon distance. So you can talk about averages and use cosmological models where you smooth things out. Whereas if you're in a mountain landscape, then one big mountain could dominate the view. It doesn't make sense to talk about averages. So we couldn't really do cosmology using the standard models if Q was too large. And lambda, the cosmological constant, again, this is a number which is which can't be too large, because in our present universe, galaxies are formed before it takes over. If it takes over too early, then this would happen. And although I have to rush this a bit, this is a picture due to a paper by Mario Olivia and myself, which sets the anthropic range, this triangle, where as a function of Q and lambda. If you had a universe that was more rough, bigger fluctuations, bigger Q, then of course structure would turn out earlier, so you could tolerate a higher lambda. So if you take these two parameters, then the higher Q is, the higher lambda could be before you lose the possibility of having galaxies. Well, so Q and lambda are constraints in that way. Now, let me turn to another thing. If we want to have a universe where complexity can occur, then we need some sort of chemistry. We need a periodic table. And we need a way in which these chemical elements could be made. And as we know, these elements are made through nuclear processes in stars. And they're made there because we know this is the famous binding energy as a function of mass. And we know that you gain fusion energy synthesizing the elements up to iron. And we know in stellar evolution that stars evolve differently depending on their mass. And one important thing which we have learned in detail, but first was conjectured in the 1950s, is that a big star before it explodes has a sort of onion skin structure where its hotter inner layers have been processed further up the periodic table. And then it flings out this material into interstellar space, and then that material condenses into new stars contaminated by that debris. And this is a wonderful picture, a wonderful scenario, and the people who developed this in the 1950s were these four people: Margaret and Geoffrey Burbage, Willie Fowler, and Fred Hoyle. They wrote a classic paper in 1957 where they spelt out the different processes whereby the elements that we are made of could be made in stars. There were some gaps which have been filled in later, but they got all the basic scenario, and they gave us this wonderful idea that we are literally the ashes of long dead stars, or if you're less romantic, we are the nuclear waste from the fuel that made stars shine. And there are quantitative details in that the proportions of the different elements shown here are explained quite well in terms of this theory. Oh, and incidentally, Margaret Burbage, shown there. This was taken for Willie Fowler's 60th birthday in 1971, I think, in Cambridge. He was a model train buff. He was given this. And Margaret Burbage died 2 months ago, aged 100. And this was a picture of her taken on her 100th birthday, showing her with Christmas cards. So she was the last survivor of this great group that really told us that we are made of the ashes of long dead stars. So that is our universe. And of course, lots of people have calculated how sensitive the productive elements is to particular features, to resonance in the carbon atom and things like that. And in particular, Fred Adams has written papers on this recently. But I want to just take an extreme scenario, what I call a nuclear-free universe. What would be like if you switched off the strong interaction, or if there was no stable nucleus apart from the proton? Well, you'd still have cooling due to atomic hydrogen. And indeed, if you kept having us the same, then you would still form galaxies and you'd still form stars. And stars would contract, but since there's no nuclear fuel to turn on, they would go on contracting until they got to the Chandrasekhar limit and became white dwarfs. Or if they were bigger, they go into contracting until they became black holes. And in that process, they would produce not much less energy than they do now, because if you contract to a white dwarf, then you get the binding energy of a white dwarf, which is about 10 to the minus 3 mc squared. And if you contract to a black hole, you might get even more. So this universe, nuclear free, would have stars in it. They would shine quite brightly. You could even have large Jupiter-like planets. And the universe would be quite bright, but there'd be no chemistry, no rocky planets, and no life. Except maybe if you do science fiction, Fred Hoyle's black cloud, just a big cloud of magnetic complexity. You know, you could have that. So this universe, the nuclear-free universe, would, in a sense, bear the same relation to our actual universe that a marble statue bears to a human being. In its gross features of having stars and galaxies, it would look just the same. but to be no possibility of any complexity. Well, I mean, I could go on exploring these counterfactual scenarios, but I think it's helpful to realize what happens if you just tweak these numbers. So I go back to the question, is the existence of a multiverse, which is the only context where this stuff has any scientific relevance, is that a scientific question? And I think, as I argued before, it's speculative science. It is science in that we could perhaps test it or have evidence for it if we knew more about the physics at 10 to 16 GeV. But I want to go back to some even earlier history, and in concluding, this is Kepler. And of course, Kepler believed that the orbits of the planets were governed in their ratios by beautiful mathematics. They were related to the Platonic solids here. And of course, he was disappointed that wasn't the case. We now, of course, know that the orbits of the planets are results of very complicated actions over their history. There's nothing fundamental about them. And of course, the consequence of some of these ideas of the multiverse is that our quest for unique interpretations for the strength of gravity and things like that may be a forlorn quest for the same reason. It may be that there are different Big Bangs where these numbers are different, and that we just happen to be in one which is in the anthropically allowed region. Just as now we would say that we're not surprised we're on a planet that's on a fairly circular orbit where water can exist going around a stable star, but there's nothing more to it than that. So it could be that we will have a theory where we have to accept that we'll never really have any fundamental understanding of the fundamental laws any more than we will have a fundamental understanding of the planetary orbits. To address this question of whether the multiverse is correct, then we will, of course, need to have a big progress in theory, and whether we get that this century, I don't know. In fact, about 10 years ago, I was on a panel at Stanford University where we were asked, how much would we bet on the multiverse concept working out? We were asked to calibrate our views on the scale, would you bet your goldfish, your dog, or your life? I said I was nearly at the dog level. And Andre Linde, who had spent 25 years of his life developing the multiverse theory, he said he'd almost bet his life. And on being told this, the great theorist Steven Weinberg said, well, he took it quite seriously. He'd happily bet Martin Rees's dog and Andre Linde's life. Well, Andre Linde, my dog and I will all be dead before this is settled. But it's not metaphysics. It's highly speculative, but it's exciting science, and it may be true. Now, just before finishing off, I want to say a few remarks which are aimed mainly at the younger people who may be listening today. I want to emphasize that although I'm an armchair theorist and theoretical ideas have been important guides, most astronomy, most progress is due not to armchair theory, but to others. It's been helped greatly in the last decade or two by the growth of numerical computations, because whereas analytically you can only consider very simple models, now we've got experts who've been able to do simulations of galaxy formation. I've showed you some of that, but also of strong field general relativity, which has been important, obviously, to interpret the LIGO results, and to understand relativistic MHD, to actually understand the movie I showed you of gas flowing around outside a black hole, and supernovae, and stellar evolution, and plasma physics. This is all important. But of course, these virtual experiments are not subject to real experiments we can't do, and that's why we are going to depend in the future for our progress on better instruments, just as the progress since the time of Einstein and Eddington has been entirely determined by the fact that we've got better instruments on the Earth and in space. So these is just a sample of all the instruments that we're going to have in the coming decade or two. And I think through those, not just through armchair theories, we're going to be able to understand better some of these ideas. And I end up with this picture. This is Edwin Hubble, a very heavy smoker, as you can see. And he said in his book, written in the 1930s, only when empirical resources are exhausted should we venture into the idle realm of speculation. So that's perhaps a good maxim on which to finish. So thank you very much for listening.
Thank you very much indeed, Martin. What a fascinating talk. And the frustrating thing about Zoom is that one can't really applaud in real terms. You can turn on symbols, but also can't laugh at your jokes. And it was what a fascinating story it was.
I don't know if those are still there.
Well, everybody's there. You had more than 200 people on Zoom and another 200 people listening to you on YouTube from all over the world. And right now, for the people on Zoom, if you are all right with it, I can invite questions in the form of raising your hand. People who are here, if you go to the participants window and you raise your hand, then I can admit you one by one, and you can turn on your audio and video if necessary and ask a question. If Martin's okay with that, let us start with, we have Swagat Mishra, one of our students here, who's asking the first question, and I'm unmuting Swagat so that he can ask his question. Swagat, go ahead. Swagat, go ahead.
Yeah. Hi, Professor. I hope you can hear me. Usually the anthropic bound is given on lambda and this fluctuation amplitude Q separately, and you showed a curve. Isn't it possible to combine both of them, like some kind of a ratio of them as one quantity, because that will be important for structure formation?
Well, indeed. In fact, that was, I rather rushed through it, but the slide of my, for my paper with Livio did precisely that, which showed that triangle. It's indicated that if Q is larger, then the lambda, which is allowed, goes up as the cube of Q. Because if you raise Q from 10 to the minus 5 to 10 to the minus 4, then structures condense out at a redshift factor of 10 higher, when density is 1,000 times higher, and therefore you can tolerate a lambda higher. So in fact, I won't go back to it now, but that diagram did indicate that the allowable range of lambda is dependent on the cube of Q. And so really, since I said that Q can vary from 10 to minus 6 to 10 to minus 3 and still allow a complicated universe, that means that lambda could, in those universes of high Q, be much higher. And of course, if we had a really, really perfect theory, we would perhaps understand any correlation between those. All we can do now is say that there's this area which is allowed on this graph where we plot those two quantities. But obviously, the larger Q is, the earlier fluctuations condense out, and therefore it would take a much stronger lambda to inhibit that from happening. So crudely speaking, the maximum lambda goes as the cube of the Q.
If you want to guess the probability distribution, would you take a flat distribution for this quantity?
Well, of course, in his classic paper, Weinberg did take a flat distribution, and he then said that the actual value of lambda was at about the 10th percentile of the allowed range. But I think we have no estimate for that. So in order to actually apply this and ask, are we in a typical anthropically allowed universe or not, then we'd have to not only have a theory which we can take seriously, but also a sort of measure on the relative probability of lots of other theories. So I think we're very, very far from being able to do that and ask whether we're in an extreme model or not. Let me give an analogy. Going back to Kepler, where if you didn't know much physics, you would observe that our galaxy, Earth, has an orbit around the Sun where the eccentricity is fairly small. It's about less than 0.1. And we're not surprised, because if the eccentricity was, say, 0.5, then water would boil every 6 months, etc. Okay, so we're not surprised that the eccentricity is small. But supposing that the Earth's orbit had an eccentricity of 10 to the minus 6, then you'd want some other explanation.
Some physics would
explain. There's no anthropic reason why it has to be quite so circular as that. And so we may be in a position of that kind. It could be that the anthropic constraint is very wide and things look as though they're more finely tuned than that. But my main point is we're a very long way from being able to place a measure on the relative probabilities of different sets of constants if there is a multiverse.
Thank you, sir.
Thanks very much. Can we move on to the next question? We have Nikodem Poplavsky. Yes, go ahead, please.
Professor, thank you very much for a great talk. I have a question about a multiverse. So there is an old theory called Einstein-Cartan theory, in which space-time has not only curvature but also torsion. And Sciama and Kibble in 1960s shown that torsion couples to fermions. And then in 1970s, several scientists showed that spin and torsion can violate energy conditions, the energy condition theorems, and prevent singularity, which means if a black hole forms, it could be possible that matter inside the black hole does not form a singularity, but instead create a baby universe. So it could be possible that every black hole makes a new universe, and basically we would have a multiverse without Linde bubble inflation, but through black holes. What do you think about this idea?
Well, I mean, of course, I don't know about the torsion idea, but of course, I should have emphasized more clearly that I took the Linde model just as one example. And of course, as you know, people have discussed what you've suggested, that collapse may lead to a new universe, and there are lots of other models. There's one by Ranzel and Lisa Ranzel et al. About the two universes, and there's the other idea, which is that there are lots of three-dimensional spaces embedded in some four-dimensional space, which is rather like one dimension up from having a insect crawling around on a sheet of paper, thinking that's their universe, and not being aware of another population of insects on a parallel sheet. So there are lots and lots of manifestations of the multiverse. I just took the Linde one as an example, but I think the key question is, do we have a theory which tells us the extreme physics so that we can decide which, if any, of these scenarios works, and then can we check whether it allows different physics in the low energy world, and can we check it? But I should have said that Linde is just an example, and there are lots of other variants of the multiverse idea.
Now, could we astronomically verify a hypothesis that our universe is a baby universe?
I don't think. Some people like Penrose have claimed that we can find some indirect evidence in the microwave background for some versions. I don't know, but I think what is more likely to me is that we will have a theory, grand unified theory or something, which maybe some variant of string theory, maybe something else. And if that theory gains credibility because it predicts something about our low energy world, like why there are three kinds of neutrinos, or why the standard model is correct, or something like that, then we'll infer there's something in that theory and take it seriously. And then we will take seriously other consequences of it. And if one of those consequences is that the infraton potential has the properties that Linde wants, then we would have reason to take his idea seriously. Rather, as I said, because we have tested Einstein's theory in lots of contexts, we believe what it says inside black holes to some extent. So I think we've got to have a theory which works under the extreme conditions relevant to the early Big Bang, and we've got to have some way of gaining confidence in that theory because it explains some things we can test, and then we will take seriously its implications even in domains where we can't make direct observations.
Thanks very much, Martin. We have another question from Sanjit Mitra after this. Sanjit, I've unmuted you.
Yeah, it's a very nice talk. I also felt quite a bit excited to see the signatures. So in order to, to see whether we can, whether there are multiverses, one way would be if the multiverses, multiple universes interacted. I mean, is there any, did anyone consider whether our universe can interact with another one if they exist at the similar times? I mean, and also like, when I see this picture of multiverses, they are like different bubbles which are not in contact. Like, why is it so? Like, they could be also sort of, touching each other, right? I mean,
yes. Well, let me say that picture was just a cartoon, which is like a 30-year-old cartoon from Linde. So that's just one of many models. And of course, there are lots of different versions. Some have linkages, others don't. And of course, it's not clear you can define a single time coordinate that applies to more than one of them. We just don't know. But as I said, there are some theories which do imply a connection. I think the idea of Lisa Randall does allow some possibility because they explain that gravity is weaker than the other forces because it leaks into the extra dimension, as it were. But there's no firm way. So as I say, I think what we're going to need is a better theory which applies to our low energy microphysics, and then we'll take it seriously. There have been some claims, rather dubious, to find circles in the sky and all that, which are evidence of impact. But in most theories, you wouldn't expect to find that evidence. So I'm not convinced that we will have astronomical evidence.
Okay, so we have another question. Thanks, Martin. Another question from Durga Teja next. Go ahead. I've unmuted you.
Thanks, sir. Myself, Teja, and I'm working as a school teacher. I'm layman in physics, but I'm curious about learning. So my question is about right now, like researchers say that expansion of the universe is due to dark energy, and they say that when the separation between the matter is very much high, then only that dark energy can expand the universe. But at the beginning of the universe, when we go to the at the beginning of the universe, dark matter is not separated too much. Then what kind of force expanded the universe, or what kind of energy expanded the universe into such big extents?
Yes, I didn't hear you very well, but I'm saying that indeed there is a theory that the dark energy is dominating the expansion of the universe now, and if you were to come back in a trillion years, you'd find a very dark and empty universe because all the galaxies except the remnants of us and Andromeda would have disappeared over the horizon. But then also, to follow up what you were saying, in the very early universe, theories like inflation imply that there was, in effect, a huge amount of dark energy which drove the expansion. And so that our universe expanded from a microscopic size to something the size of an apple or tennis ball in 10 to minus 36 seconds. So that's extreme. But as I say, we won't understand the dark energy until we understand the nature of space, which probably has some sort of grainy microstructure, just as we learned in the last 200 years that all solids have a microstructure on the atomic scale. Space itself probably has those structures, but on a scale which is far too small for us to observe directly. So that's why it's so difficult. So these are just speculations at the moment.
Thank you very much, Martin. It doesn't seem like any other hands are up right now. Yes, we have another one.
Yes. Okay. Can I say, it's interesting that everyone talks about the multiverse, not about the more conventional physics. As a sign.
That's right. Very interesting that all
like the speculation. But can I just say one thing about telescopes? Telescopes that I know India's involved in are crucial, and you're involved in gravitational waves and all that. And this is really very exciting. And I think space exploration through robots is going to be important. I've just been writing 2 articles. One is about why the case for sending people into space is getting weaker all the time, because it's very expensive, and the robots are getting better. So I think that space should be done by robots and automatically, etc. I'm doing that. But also, I should say, I've got a challenge, and Selmak, maybe you can send me some advice. The Scientific American magazine has its 175th anniversary, and they're having a special issue in September on science in the last 175 years. But I've got to do the whole of astronomy in 5,000 words. And it's rather interesting. If you go back 175 years, it's an interesting time, because before that time, there was only gravity and positional astronomy. That was a time when it was famously said we'd never understand what the stars are made of. There is some special essence. So modern astrophysics started with spectroscopy, when Huggins and people in the 1860s realized that the stars are made of the same stuff as the Earth and the solar system. And that was really the first real astrophysics, as opposed to just applying Newtonian gravity, which of course had been applied before that. And so I start my article by saying a bit about understanding what the stars are made of as the first bit of astrophysics, and then leading on to Einstein and all the rest. But
the discovery of helium would come very soon.
Any suggestions on how to fill my 5,000 words?
Well, we can discuss this. Thank you, Martin. We can discuss this maybe offline.
Yes.
There are some questions coming in. Can I ask you a few? Here, Kandu has a question for you. He couldn't raise his hand. So, Kandu, can you unmute yourself and ask?
Yes. I'm trying to ask, I was wondering, one of the things which happens, you understand stars maybe, even galaxies, but the formation of black holes in the centers of all galaxies is something which always seemed fairly difficult for me, to form supermassive black holes. And you have thought a lot about it. Mm-hmm. So do you have anything to say further about this?
Well, yes. I mean, as you know, I sort of flow diagram about 40 years ago of how the various scenarios whereby this might happen. And I think there's still a variety of options. I personally think that people worry too much, because they make one invalid assumption. They make the assumption that there's a limit to the growth rate of a black hole set by radiation pressure, which pushes the matter out if it tries to accrete. And then you get the so-called Eddington limit and all that. I think people are starting to realize now that that's not very relevant, and that if you smother a small black hole in a lot of material, then it can accept that material very fast, and most of the radiation gets advected in rather than pushed out. That's a slightly technical answer, but for that reason, I think people have worried too much about how very big black holes can grow and be present even at high redshifts. I think they need to accept mass at a high rate, and they can do that at a very high rate by, in effect, advetting in the radiation, so it doesn't have to be radiated. So in other words, the Eddington limit and the associated growth time scale, which is often quoted, is, I think, being misapplied even when you don't need to apply it. So, well, it's not saying we understand the details, but I would say it's not a big puzzle how you get massive black holes once you've got a galaxy. When gas falls into the center, loses angular momentum, etc. And people are starting with computer simulations to address this. But I think it is a bit frustrating because in our galactic center, one would like to understand how the black hole is growing, etc. But the trouble is that you've got to have simulation with a big dynamic range, because you've got the radius of the black hole, but its sphere of influence is millions of times larger. Okay, if you go out to the place where the velocity of orbit is below 300. So it's a big dynamic range. And just as it's very hard to understand star formation in detail, because there are no really good calculations that span all the density range from an interstellar cloud to the actual star, so it's rather hard to go all the way from a sort of a primordial galaxy with a high density to the density around the black hole. But it's the big dynamic range that's involved, which I think will inhibit more exact calculation. But there's lots of work being done by various groups. I mean, Ramesh Narayan's group, for instance, has done some nice models for disks around black holes, and indeed how magnetic fields get captured by them. But I think it's a dynamic range which is the problem.
Thanks, Martin. So you think even from stellar mass black holes you will get to 10 to the 9? Or do you need 1,000 solar mass or the seed black holes?
Well, again, I don't know. I think you. I don't see why if the supply of gas is sufficient.
Right. Okay. Fine.
Then the Eddington limit is not relevant, because if it's smothered and the angular momentum could be got rid of, then there's no limit to how much gas can be accepted by the black hole. And so I think it depends on the mass of the first stars, and as you know, it's conventionally thought that the first stars are more massive than present ones, and so you could start with those. But I think probably there is some compromise. Probably in the sense of some galaxies, you get a mass of say 10 to the 5th solar masses or thereabouts collapsing in one go in the center, and then accreting from there. We don't know. But all I'm saying is I think it's something that people have worried about too much.
It's okay.
Yeah.
Thanks.
Martin, can I squeeze in another question from your YouTube feed?
Yes.
You had about 200 people watching you there, and many questions are coming up there, if you don't see. So one of the questions there is from Tejinder Singh, is asked whether you have an assessment of the discrepancy between the value of the Hubble constant between Planck data and the other supernovae data and various other distance measurements.
Yes, I'm afraid I don't. I mean, I talked to my colleague George Statue, who is a great expert, and he, of course, tends to think that the Planck value is nearer the truth. So I wouldn't like to comment. If you ask me to bet, I will bet that the resolution will be a dull one, in that they will find that the errors in the supernovae and the extreme giant brown stars and all are a bit larger than people thought. So I will bet that it'll be a dull resolution. But of course, I hope there isn't. It would be great if this was a serious discrepancy, which did lead to some new idea. But of course, as you know, it's been rather hard to think of any new idea. People have had ideas of having dark matter which decays into something relativistic at some time, etc., which could change the expansion rate of the universe, but none of them work too well. So I should say I'm not well qualified to give a detailed assessment, but if you ask me to bet, I would bet that there will be some reconciliation, but I hope not, because we always hope that there's something very exciting, but of course the most exciting and newsworthy theory is not always the most likely one.
I think that's a good note to end today's session. Thank you very much, Martin. And thank you very much for everybody for being present today. And there is an applause button down there for reaction.
Yes. Well, thank you for the invitation, Sir Max.